Whenever we have log base a of 1, it's 0. Whenever we have log base a of a, it's 1. And what we're looking at here is remembering that anything to the 0 power is 1. And then a to the first power is a. So what we're going to do is pick these values within any type of log just to get 2 ordered pairs. Because really, once we start looking at the 2 ordered pairs, we're going to identify the curve, and we'll be able to also identify where our asymptotes go. Okay? A lot of this is going to break off of what we did last year in Algebra 2, and then kind of go. It's actually, from what I was reading in the book, it's a little bit easier than what we did last year. There's a little bit less work. They don't change the base on you as often. So what we're looking at here is anytime we're going to graph, sorry it didn't show up as nice, whenever we're going to graph y equals log base a of x, you can always think of it as we're going to pick values for whatever this base is to make these 2 properties work. And that's how we're going to get our ordered pairs. It's really that simple. There's really not much else to it when it goes through. What's up?
Is there like a little indent you see at the bottom?
No, it was just when I tried to circle it, it just kind of put it through, that's all.
Alright.
So, let me show you an example here. I don't want to do that one. Just let's graph y equals log of x. Just to look at that. And if I want to look at just log of x, what I want to do is think about, well, what's the base?
10.
It's base 10. And why is it base 10? It always is. It always is. If it's not written, it's automatically implied that it's a base 10. So I know that my a value here is going to be a 10. So what we're going to do is we're going to look at values. Oops. Log, I'm going to write it as a base 10 of 1 equals 0. What I'm doing here is I'm picking a value of x to generate a value of y, which means log base 10 of 1 is going to equal 0. So I know that this first ordered pair would be at, well, this is my x, this is my y, so it's going to be at 1 and 0. Okay? And then if I do that again with the values of, if I pick 10, because my value of a is 10, if I choose, that's going to equal 1. So that means my other ordered pair would be at 10 and 1. Yes, ma'am? That's the ordered pair. And when x is 1, y is 0. Because all I'm doing here is using this here. I'm picking these values of what I'm choosing here and here. I'm always going to choose 1, because no matter what the base is, if it's log base 3 of 1, it's 0. It's a very easy thing to do when you work through them. Now when we throw an h and a k, then we're just going to make it equal to 1 by choosing that value that creates that ordered pair. Okay? Same deal with whatever your base is. You're going to choose whatever your base is as well as the other ordered pair. So if you start to look at this in terms of the graph, just move this down. We had an ordered pair at 1, 0 and 10, 0, or excuse me, 10, 1. Now, one of the rules that I don't know if we really talked a whole lot about when we're graphing logs, is that we have these old values, is that our domain is always going to be greater than 0 when it's just log of x, whatever our base a is, okay? Our domain is going to be x is greater than 0. Oops, it looks like a 6, sorry. All right? Which means, is it ever going to equal 0 if it just says it's greater than? So if something's never going to equal 0 and it's going to always approach it, what is it approaching at 0 then? It's approaching an asymptote. There's going to be an asymptote, a vertical asymptote, at x equals 0. Okay. That asymptote will move as we move the logarithm. When we add that, you remember h's and k's? We move it horizontally and vertically. We'll move that vertical asymptote to some value of h as we shift it around in a little bit. Okay. Now, since our a value is greater than 1, this comes back from last year in Algebra 2. If a is greater than 1, your graph is moving up and right. So I know that this is moving this direction. It's doing that. So I'll write up some rules on the side here. But when we shift it, we'll add the h and k, see if you remember what this looks like. When we shift these things, our vertical asymptote is going to move h. Okay? So we're going to wind up with x equal h as your vertical asymptote. Your domain is going to be when x is greater than h. Excuse me. The range is always all real because there's no horizontal asymptotes with these. If a is greater than 1, it's up and right. So if your base is greater than 1, it moves up and right. If the base is between 0 and 1, it's moving down and right. Now it is possible for this thing to be reflected to the opposite direction if it was negative. And as we start to play around with some of these graphs, you'll see how that works. It's pretty easy as you start to work through these things. Just really all you need to remember as far as graphing is concerned when you're working with logs is that log base a of 1 is always 0, and log base a of a is always 1. So one of the things that I remember a lot from last year when people were having problems working with their asymptotes and trying to figure out ordered pairs as far as to make these numbers very easy to work with was how are you going to create these scenarios? That was something that happened a lot. I want to walk you through a couple of those examples before we get into a lot of the shifting of the graphs, okay? So if I have log, let's say it's just log, we'll just go base 10 for right now, of x minus 4. Okay. And I want to create these two scenarios. I need to pick values of x that will make these work.
So,
5, right? Yeah. What I'm trying to do here is I want to create
wait, I have a question.
yeah.
Say if you, okay, then I would say 14, right? Okay, then you get log 10, 10, which would be log. This is log. Is log an answer?
What's that?
Is log an answer?
What do you mean, is log an answer?
Oh, wait. No. You see right here? Yeah.
What you're trying to do is you're trying to create these two setups to get your ordered pairs for the graphs. And it all stems from being able to do x minus 4, and I want it to equal 1. I want x minus 4 to equal whatever my base was. So I'm solving for x in both of those. Do you guys vaguely remember that from last year? Thank you, Tessa.
You seriously
So I set this up. Buddy!
Katie, who's there?
I saw your face, you were like,
So obviously what I'm doing here is I'm setting up one of them I needed to equal 1. So what value of x gives you 1? Right. So I know that I have an ordered pair that at 5, it would be at 0. If x is 5, my y value becomes 0. All right? Because if I put 5 in here, I get 5 minus 4, which gives me log base 10 of 1, which is 0. And I do the same thing with, I want to make x minus 4 equal to my base, which is 10. So what would x have to be there? 14. So the other ordered pair would be at 14 and 1. Because if I put 14 in, I get log base 10 of 10, which is 1. Okay. That was the idea of a lot of times when we worked through a lot of these problems last year when you were graphing. You had to come up with the 2 ordered pairs to make it work. And in order to get those 2 ordered pairs, you had to get that log base to go. I want to create this because I know whatever I have log base of whatever, if it's of 1, it's going to equal 0. So since this part is x minus 4, what value of x gives me 1? So if I use 5, I get 5 minus 4, so log base 10 of then 1 is 0. So the ordered pair would be at 5, 0. Okay? And I do the same idea with the base a. Since my base is 10, I set this equal to 10 to solve for x. And that'll give me 1. My y values here should be these guys to start with. Okay? That's just the quick simplifying my way through. When I throw a k value in, then they just move up and down. But this is our first little simplification thing. As far as like ordered pairs would be concerned, if you happen to have something where you had to go and, let's say you had log base 6 x plus 1 plus 3. You still want to create the ordered pair. So first thing you would do is, all right, how do I make this equal to 1? What would I pick for x?
0.
0. Okay. So if I substitute in 0, I get log base 6 of 0 plus 1. So I get log base 6 of 1. Well, what's log base 6 of 1? 0 plus 3 gives me 3. So this ordered pair would be at 0 and 3 because it had that vertical component to it. All right? That's all that meant. Okay. That's what we did. We did a lot of that of trying to create our own ordered pairs to make these things work pseudo-clean. Let's try another one. Let's graph this one. Oops. What did I have? Let's graph this one. Log base 4 of x. Sorry, that x looks like it's an exponent. Sorry. There. Is there an h component? Is there a k component? No. So we know that h and k are both equal to 0. So h is 0, k is 0, which means where's my vertical asymptote?
0.
It's 0. Good. I have a vertical asymptote at h, so it's going to be at x equals 0. Oh, excuse me. Yeah, x equals 0.
Oh, wait. Over there on the board where you put x
Yeah.
Okay, I was confused, I saw it, because I didn't know if that went together.
Yes.
Okay.
Yeah. Because I know right before I had it from what we were doing in algebra, it was something different, so we're also asking for it. So. One of the things that we did before when we had asymptotes on the axes, one of the things you can do is just do this. Because you know how the asymptotes are always dotted vertical lines? If you want to just put a little arrow and say that it's dotted, because that's where your asymptote is, that's okay. I'm fine with that. So then now I want to create those two scenarios. So when I do that, in order for me to get 1 for x, what do I substitute in for x? No! 1. So the first ordered pair, the log base 4 of 1 is 0. So I know that at 1, it's 0. What's the second ordered pair I'm going to use? What? Yeah, 4. The second one would be at 4, because I use the same base. Log base 4 of 4 is 1. Our value of a was greater than 1, so it's moving up and right. We have our asymptote. Our asymptote was here. Kind of. I'm just going to move it up. There we go. And that's what we do. We label out our two ordered pairs and we go. Shall we try and do one with an H and a K?
Yeah.
Okay. Here we go. I know, we're living dangerously. Okay. All right. Yeah. Let's graph that.
So this would be upcoming.
Absolutely. That's why I keep saying, if you fall back onto those two properties, everything else is just ordered ops. It really is. You just have to know those two. So if we walk through and want to graph log base 3 of x plus 2, all minus 4, first thing I want you guys to do is label h and k. Well, not a, but or h and k. Our h value is what? -2, good. H is -2. K is -4. Which means I have a vertical asymptote at x equals -2. So now we have to make the scenarios work. We're going to need to figure out, I want to make log base 3 of 1 to equal 0, and I want to make log base 3 of 3 to equal 1. Well, how do I make this work? What would x have to be to make that into a 1? -1, very good. So if I use -1, I get log base 3 of 1, subtract 4. So this becomes 0 minus 4, which is -4. Very good. So I know that that ordered pair then becomes -1, -4.
What?
Yeah. Because
Back up.
-1 is
Where did you get, okay, so 1 minus 4,
Mm-hmm.
and then,
It's not 1 minus 4. This is log base 3 of 1 is is an exponent. Think of it this way. It's one of the exponent rules. When you're doing please used by Gary and Sally, think of a logarithm. Because a logarithm is nothing but an exponent. Treat that as an e when you're in your PEMDAS thing. So log base 3 of 1 is automatically 0. What I'm doing here is, I'm trying to chunk this part first to equal this.
Okay.
Because then I can simplify it further. You might have done it the long way last year where you plotted the parent, then the shift.
Yeah, we did.
Here will be okay, just to kind of go for it.
Okay.
All right. So here, I know that if I use -1 for my value of x, I'm going to get -4 for my value of y. That's what we were doing. That's my point. And I'm sticking to it.
No, like what's the?
-1, -4. Because she said that's my point, and I said yes, I'm sticking to it. Is the point. It's log.
Why is it negative 1? Why wouldn't it be 0?
Right. What value of x
Oh.
created this?
Okay.
I chose -1 for x.
Okay.
That's what I get for leading off the day with cartoons.
I liked it.
Thank you.
We just start every day with a cartoon. Schoolhouse Rock, don't they have math ones?
I'm sure they do. Now I want to create the scenario of log base 3 of 3. What value of x gives me a 3 within my parentheses? A 1. So I know now if I choose log base 3 of 1 plus 2, subtract 4, I get log base 3 of 3, which is, it allows me to simplify that log out of there. So then that means at +1, my x value is -3. And it's, the a value was positive, there's no leading term or anything like that, so it's moving up and right. It's kind of the easiest way to do this. Just by falling back into those two basic setups. Whoa. Saw you too. Beautiful. Yes, ma'am. You know, I was waiting to see how long it takes me to figure that out. Figure it out.
Talking about the answer.
No. Oh, I can't spell asymptote.
Oh, okay, so,
I-
yeah, I was gonna say
It's not.
7,000.
It's sometimes it's Y or an S. That dotted thing you can't go over. How about that? Really, the only other part that's in this secondary part of 3.2 is how you rewrite e's and natural logs. Remember, as we get into the last little bit, for natural log, the natural log was when you had log base e of x equal to natural log. All right? Whenever you had that base e, we use a little bit more of that base e. We'll do a lot of it tomorrow with some of the worksheets and stuff that I have for the PERT problems, graphing with exponential. It's really pretty easy to work with. What happens with natural log stuff is how you undo it. You see that a lot more in equations. For example, if you had to undo a log, you'd have to exponentiate it and they drop each other through. But one of the things that the book asks you to do is to write something from exponential form into natural log form. Okay. For example, if I want you to write something from exponential to natural log form, what do? Well, let's say we have this. I want to rewrite that as a natural log. Take a deep breath.
I bet you annoying.
How would you undo E? Natural log. And to undo natural log, you E it. Basically, all this means is that the natural log of 7.389 and change equals 2. That's it. To be honest with you, I'm not quite sure why the book emphasizes this as much as it does, but there's a good chunk of problems about how do you rewrite between the two forms. Again, if it's E, let's say it's E to the 5th and it equals 17.4, to write that as a natural log, it would be correct. That's it. I mean, this is not, that's not the actual value of it, but I'm just saying, that's all that is. What's that? 2K plan. That's it. And then you do the same, you do the exact opposite, go the other direction. That's really it. Do you have the natural log of 10 equals, what do they have? 2.302. And I want to write that in terms of E. Well, that just means that 10 equals E to the 2.302. Yeah, exactly. That's it. You just switch it. Which one doesn't have the E? If you're going from natural log to E, well, the one that side that has the natural log is the answer. The other side gets E. One side has the E, the other side gets natural log. That's about as goofy as this gets.
Any other ones I wanted to show you? I don't think there was.
Yeah, I think we're good. On this one, we did what? We did through 30 yesterday, I think? Was that right?
We did like 3 through 30.
Every
30,
every third.
Yeah.
Okay, let's do this then. So the secondary part then, let's do 32. So this is still page 236-ish. 32, 34, 36, and then, I want you guys to see if you can figure out what happened to the graphs on 39 through 44. What these are doing here is that the basic graph started out as log base 3 of x, and then they were shifted. They gave you the graphs themselves, and they were wanting to figure out which one of them was shifted a certain way by moving an h or a k, or inverting it with a negative. Okay? So see if you can figure those out. Oh, I got a couple more.
Yeah, this was here.
Yeah, we'll do that. Yeah, then we'll do. And I want you to graph 73 and 74. Okay? Yeah, just do the odds on those. Then we can check to see if you got it right. It's just rewriting, really. Those will take you a couple minutes. Yeah. Just so much you can involve. Okay. These are shifted versions of this. You were on your phone at that point in time. At least you weren't driving. This is the parent function. These were shifted versions. Yeah, work on those. We'll go into some more of the word problem stuff tomorrow. A couple more graphs of the exponential graph. We might do a couple of natural log graphs. I don't remember it. I got to talk to Mr. Fontana to see if they emphasize that a lot in this class or not. So we'll go from there. I was looking at how this stuff pairs itself out. It looks like normally they quiz after section 3. I don't know how long it'll take us to get through section 3 with properties, changes, base, rewriting, quotient rules. That usually takes a little bit of time. So I honestly don't think we'd be quizzing until maybe next Tuesday at the earliest, just so you guys know. All right? No, I don't think we'll get anything this week. All right? Oh, sorry. Let me just pause.